All right, so we need to talk about the exam. Do you want it on the weekend or during the weekdays? I should be done with the material on Wednesday. We should not have a class on Thursday. So Wednesday should be the last day. Then I can give you the final. Will be like 8 hours. So we need to decide, do you want it on a Friday, Saturday, or Sunday? I know someone wants to have it on a Friday. We can work that in individually, but I assume some of you work during the weekdays. So so let's do it on how about Saturday? And for the person who can only do it on a Friday, that will be fine. It will be accommodated, okay? Don't panic. So it will be like the same format as a midterm. I will post it, and then you upload it to Canvas. And the person that takes it on Friday, you can email it to me. I will email it to you on a Friday too. So if I am wrong about the person on Friday, please let me know, because I don't remember. If the class wants the weekend, I personally would still like to take mine on a Friday. All right, perfect, no problem. Friday is fine. All right, so let's do the exam on Sunday, all right? So we're gonna do the exam on Sunday, next Sunday, or this coming Sunday, okay? All right. I hope you did watch the video I taped for last Thursday. It is posted. So today we're gonna talk about something called Lyapunov functions. Chapter 6, Lyapunov, Lyapunov functions. Some people spell it like this. Lyapunov, L-I-A. Okay? And of course, Lyapunov is the name of the person who came up with it. He's a Russian mathematician in the 1800, late 1800, and he was looking at some systems, and people used to call it the energy function, or he did call it the energy function. But later on, after he passed away, I think he did his thesis, PhD thesis on the energy function. And after his death and later on, people found out that it has a lot of use, and it was so valuable and important in the qualitative analysis of stability. So they start calling it in honor of his name, Lyapunov functions. Okay, I prepared this spell. All right. So what is a Lyapunov function? Lyapunov function, you have a system, and you want to show that the system is stable. That means you have an equilibrium solution as before. And we did through the eigenvalue, eigenfactors, if it was systems, to look at the stability of the solutions. However, if you have a nonlinear systems and the linear system is only stable, or then the linearization, if you've seen my last video, will not work. So one of the resort is to use the Lyapunov functions. Okay. So this is chapter 6, section 6.1. And the mystery of Lyapunov function is it will not be presented to you. You'll have to come up with it, and each system may have a different Lyapunov function that works better. but mostly they're gonna be quadratic, like polynomials depend on how many variables you have in the systems. So most likely it's gonna be polynomials if you have a polynomial systems or something like that. Okay. So we're gonna say let G be a subset of Rk, and we're gonna define xn plus 1 equal f of xn. And that is 6.1. Okay? And here, f from G into Rk is continuous. We're gonna assume system 6.1.1 is autonomous. That is f of x does not explicitly depends on n. For example, if I have xn plus 1 equal x squared of n plus x of n, that is autonomous. Okay? On the other hand, if I have xn plus 1 equal nx squared of n plus xn, this is non-autonomous. You see, you have an n explicitly in it. Over here, you don't. You have x depend on n, but that's okay. But you should not have n out of x. Okay? So this is autonomous, because autonomous system behaves differently from non-autonomous when it comes to Lyapunov functions. All right. So we're going to assume x star is an equilibrium solution of 6.1.1. That is f of x star equal to x star. Okay? For example, we've seen this before, is x squared of n plus 2xn, and then that is your f. Okay? So you put x squared plus 2x equal x. You get x squared plus x equals 0. You get x plus 1 equals 0. So you get x equals 0 and minus 1. So x star is 0 and minus 1. Okay? I'm just reminding you. I'm not telling you anything new. All right? All right. Any questions? So we're going to do a definition. And x star, remember now, is a fixed point. Again, so we have xn plus 1 equal f of xn. That is 6.1.1. And f from a subset that is in Rk to Rk. All right? And we have that x star is an equilibrium solution. Okay? So that's what we are looking at now so far. All right. definition. All right. Let the function v be from Rk into R, be continuous. Okay. Then one, the variation of V with respect to 6.1.1 is defined as del V of xn equal to V of xn plus 1 minus V of xn. That is V. You see xn plus 1 is f of xn minus V of xn. Okay? So this is the variation of V. All right? Two, the function V is said to be a Lyapunov function. Lyapunov function. Okay? On a subset H of Rk, on a subset H of Rk, if one V of x star equals 0 and V of x is positive if x is not x star. Okay? And two, del of V of x is less or equal to 0 whenever x and f of x belong to the set H. Okay, belong to the set H. All right. Thirdly, V is said to be a strict Lyapunov function okay, on H if del V of x is strictly less than 0. You see the difference here, we said less or equal to 0. Here it's a strict. Okay? All right? So let's do an example. So go through the definition first. Reread the definition and make sure you understand it. Please go ahead and reread it before I do a couple examples. All right, so let's flip the board. All right. So example, for a different than 1, consider xn plus 1 equal axn. Okay. Then nearly here, f of x equal ax. So f of x equal x mean ax equal x, mean x a minus 1 equals 0. That implies x equals 0 since a is different from 1. So we have x star equals 0, right? So this is a polynomial, so let's consider the Lyapunov function v of x n equal to x squared of n. I'm just gonna take it to be x squared of n. Why? Well, because first of all, let's try one. V of x star equal v of 0 equals 0 squared equals 0. So that's good. And 2, v of x equal x squared is positive for x different from x star, which is 0. So that is fine too. Take a look at those definitions. Okay? So here, del Vx, all right? All right, so here, the function v is said to be a Lyapunov function if Vx star equals 0 and Vx is positive if x different from x star. Okay, so this is 1, all right? So here, as you notice, V is defined from R into 0 to infinity. So here your set H is R, okay? Because it takes all value. But for now, that is for now. We may have to restrict this one as we shall see. Okay, so let me not say H is R because I am going to determine H based on del V. Based on del V here, I'm gonna determine what H is. Now, 2. What is the variation? That is, remember, V of x squared of n plus 1 minus V of x squared of n. Or this is, if you go from here, this is x squared of n plus 1 minus x squared of n. But what is xn plus 1? Xn plus 1 is axn. Okay, so this is x squared of n of a minus 1. Correct? Actually, that is fine, basically. Okay. Oh, I made a mistake. Of course. This is x squared. So this is not correct. So this is a squared x4 to the n minus x squared to the n. So del V is equal to factor x squared out, x squared of n out. I'm gonna have a x squared of n minus 1. Why am I doing this? All right. So this is what I have for now. So what do you think? A is less or equal to 0. You see, this is a positive. Can this be less than 0? How do I make this one less or equal to 0? What do you think? So if I want del V to be less or equal to 0, that means this is never equal to 0. I need ax squared of n minus 1 less or equal to 0, don't I? And that means that is xn less or equal to 1 over a. This is what it means. Okay? So, what is the set H? So the set H equal to all the x in R such that x less or equal to 1 over a. You see my set now? Hence, on H, del V is less or equal to 0. So on the set H, it's less or equal to 0, so it's a layup on a function. Okay? You see what we did here? All right. Okay. So you see H has to be chosen cleverly. So So del V is less or equal to 0. All right. And notice x equals 0 works. If x equals 0, then this will be negative, equals 0, because this is 0. So this will verify too. So let's take another example. Now, let me take a different example. Okay, can I take, let's say, let's keep this example as is. Let's keep this example as is. And let us try v of xn equal absolute value of xn. So clearly, one, v of x is positive if x is not x star, which is 0, and v of x star equal v of 0, that is 0, that is 0. So this is satisfied. Okay? Why don't you go ahead and compute del v of xn? Well, automatically you do it from here. That is xn plus 1 minus xn. Go ahead and substitute this here and see what you can get out of it. I need you to practice. Okay? So what is this here? If I take this one, xn, so this is a xn minus xn. So that is a x. Let me get rid of the n. And that is x factor a minus 1. You see that? And so this is less or equal to 0 if a is less than or equal to 1. You see that? So what is the set H here? H, okay? Oh, I think I did before in the previous example, I think I did x squared of n. I do apologize. Okay, so let's redo this one. Let's do this one with absolute value of xn. So here the set H is all the set x such that x belong to R. It doesn't really matter. And this will always be less than 0 if a less than or equal to 1. So now let's take Vxn equal to x squared of n. Let's do that one for this. So this is okay. Let's do this one and see if we get the same result. So clear v of x is positive if x is different from x star, which is 0. And okay, 2, no, and v of 0 is equal to 0. Put 0 here. Now del v is x squared of n plus 1 minus x squared of n. That is a squared x squared of n minus x squared of n. That is x squared of n, okay, times a squared minus 1. And this is less or equal to 0 for a less or equal to 1. Same result. Look at it. Same thing. Okay? We got the same result. All right. So you see, we came up with two different Lyapunov functions. Some of you, can I take Vx of n equal xn? Can I take that? Can you answer me verbally or through chat? What do you think? Can I take this v to be Lyapunov function xn? Does it violate this? It does, doesn't it? If I don't put a restriction on x. Okay? So this is no, v has to be positive, remember. So the answer is no. Okay. All right. So here's another example. Xn plus 1 equal to x squared of n. Determine v and h so that v is a Lyapunov function on h. What do you think? Well, how about, first of all, x squared of n equal xn implies x minus 1 equals 0, x equals 0, x equals 1. So we have 2. So let's first consider x star equals 0. So each one will have a different Lyapunov function. Okay? Each one will have a different Lyapunov function. Well, for this one here, for this, we're going to take Vxn equal to xn. Why not? Okay? So, V of 0 equals 0, and V of x is positive for x not 0. So because I'm talking about this now. What about del V? Equal to xn plus 1 minus xn, and that is x squared of n minus xn, if you like, and this is x of n squared minus xn, and that is xn in absolute value will be xn minus 1. Okay, so this will be less or equal to 0 on the set H equal all the value x in R such that all the value x in R such that what? X minus 1 less or equal to 0, which is all the x in R such that x less or equal to 1. There you go. And on this set H, V is a Lyapunov function. Now, if you want it to be strict Lyapunov function, then you make the equality strict. Okay? So, all right. So now let's see if we get the same result if I take this one to be x squared of n for x star equals 0. Then del v of xn equal to x squared of n plus 1 minus x squared of n. X squared of n plus 1 is x squared minus x squared, x4 minus x squared. All right. So this is less or equal to 0 on the set H equal x in R such that x less or equal to 1. Okay? If x less or equal to 1, that will be less or equal to 0. So I displayed for you two Lyapunov functions for x star equal to 0. I took absolute value of x, and then I took x squared of n. So you see Lyapunov function are not written in stones. You have to come up with it. But since we're talking about x plus 1 equal axn, x squared of n, blah, 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 this kind of Lyapunov function will do for you. Now I will move on to system. How about Lyapunov function for x star equal 1? Well, I'm gonna say let Vxn equal to how about xn minus 1? What do you think? Well, let's take a look. V of x is x minus 1 is positive. If x is different from 1, which is x star, and V of 1, V of x star equal V of 1, that is 1 minus 1 equals 0. You see? What about del V? Go ahead and compute it for me, please. Spend 2 minutes on it. Go ahead. Let's see what you can come up with. So this would be xn plus 1 minus 1 minus xn minus 1. Xn plus 1 is, that is x squared of n minus 1 minus xn minus 1. And that is xn minus 1 times xn. Okay, no, let me factor it. Okay, let me do this. And so if I factor xn minus 1, I will have I'm factoring this one, x squared minus 1 factors into xn, x squared minus 1 times this one. So this is xn plus 1 minus 1. Okay? So I mean, you may say, how does that work? Well, I mean, let's take a look at this one here. This is xn minus 1, xn plus 1, but this is the same as xn minus 1, xn plus 1. You see? So this is what it is. Xn minus 1 times, let me make it look a little bit better. Xn plus 1, okay? All right. Absolute value minus xn minus 1. So factor xn minus 1, you'll get xn plus 1 minus 1. So you want this one to be less or equal to 0. So we need to do some work here, okay? And this is the whole idea now. So you want to be less or equal to 0. We need to figure out what the set H is, okay? So it's not hard for this one. If xn plus 1 minus 1, so xn will have to be negative and very sensitive, okay? So this will hold if xn is less or equal to 1, okay? No, less or equal to xn less or equal to 0, so we don't want that. All right, I will discuss it in more details when I do the stability theorem, okay? When I do the stability theorem, I will do this for you. All right, so this is like a Lyapunov function. If you want to use, remember before, for x star equals 0, we took two Lyapunov function, and here you can take xn minus 1 squared, and you can run through this, and you get similar results, okay? You see minus x star. So basically, in most cases, you're gonna have to take Vx star has to be x star minus 1, but x star is 1, so it will be 1 minus 1 is 0. So that is a very, very important. Okay, so now let's take a theorem and see what we can do. Okay. All right. All right. Theorem 6.1.1. Let V be a Lyapunov function for 6.1. Okay. And and let x star equals 0 be an equilibrium solution of 6.1.1. So here we are shifting the equilibrium solution to the origin. All right. So that is, what am I talking about? V0 equals 0, Vx is positive if x is not 0, and del V of x is less or equal to 0. Then the zero solution of 6.1.1 is stable. Okay? And if del V is less than 0, then the zero solution excuse me, of 6.1.1 is asymptotically stable. So that is here, this is theorem 6.1.2. Okay, so I combine two theorems together. I will come and then do an example. Okay, so I want to go back to some of the previous examples. So I'm gonna now do so many examples for you. Okay. Let me do. Okay, let me take another example here. Let's see what I want to do. Let's apply this theorem to All right, let's see what we have. Let's go back and revisit xn plus 1 equal x squared of n. And now I'm gonna take x0 equal x naught. That is an initial condition. So we know x squared equal x, mean x star equals 0, x star equal 1. Now, do you remember when we did xn plus 1 equal f of xn, and we looked at f prime of x star? Okay? So these are similar to, I mean, we could do it this way, but some cases it cannot be done that way. All right, so we're gonna use the Lyapunov functions. So let's consider x star equals 0, and let's take vx of n equal to x squared of n. Then del v is x4 of n minus x squared of n. This is x squared times x squared minus 1. All right. So if I want less or equal to 0, means x squared minus 1 has to be less than 0, or x has to be between minus 1 and 0. Okay? Now, if so, H is all the set X in R such that minus 1 less or equal to X less or equal to 0. Then del V is less or equal to 0 on H. So what does this mean? This means that if x0, which is the initial point, is in H, then the solution will not wander away from x star equals 0, and hence x star equals 0 is stable. You see what I mean? Now, if I let H equal to all the set X in R such that minus 1, such that X minus 1 less than X less than 0, and 0 less than X less than 1. So this is the union minus 1, 0, union 0, 1. If I take H to be that set, then del V is less than 0 on this H. And hence, if x0 belong to H, then solutions will asymptotically go to 0. So that means x star equals 0 is asymptotically stable. Now, can anybody answer me, what if I take x naught outside H? If x naught is not in H, then solutions will not go to 0. Okay? And in this case, the zero solution is not stable. Do you understand what we just did? Okay. What do you think? Okay. So I mean, it all depends on your initial point. So this is, you may look at this as conditional stability. It's not a global stability, because the stability depends on x naught. Where is the initial point? If there is the initial point in the set H that make V, or the variation of V, less or equal to 0, then yes, your equilibrium solution is stable or asymptotically stable, depend on what we want. But if your initial point is outside the set H, then your equilibrium solution is not stable. Now let's do the same example for x squared. Now let's take this one. Now let's try this. So for this one here, I'm gonna take it -1 squared. You see what I did? I'm gonna take this one to be my Lyapunov function. Okay? So notice that v of 1 equals 0, and v of x is x minus 1 squared bigger than 0 if x is not 1. Okay? All right. Now what is del v? Del v of xn is xn plus 1 minus 1 squared minus xn minus 1 squared. What is this one? Xn plus 1 is x squared. So that is x squared minus 1 minus x minus 1 squared. You see what happened? Okay? Oh, this is a square, sorry. Okay? This is a square. So this one is x minus 1, x plus 1 squared minus x minus 1 squared. So this is x minus 1 squared, x plus 1 squared minus x minus 1 squared. Let me take x minus 1 squared, and I have x plus 1 squared minus 1. You see that? Now, this one is always bigger than 0. So let's assume we want asymptotic stability. So del V is less than 0 where? So we're assuming x different than 1. That means this is a positive. So this is for x plus 1 squared minus 1 is less than 0. Okay? And that turned out to be x squared plus 2x plus 1 minus 1 less than 0. Turned out to be x plus 2 less than 0. Turned out to be minus 2 less than x less than 0. Okay? All right? So h, I'm gonna take h to be all this x in R such that minus 2 less than x less than 0. So on this set, so if this initial point is in H, then X star equal 1 is asymptotically stable. Okay? You see what happened? And if X naught is not in H, then X star equal 1 is unstable. Okay? So there we go. Now let's take a look at system. Any question about this? What do you think? It's interesting, isn't it? Okay. Now let us take a look at system. We are looking at system. For example, let's take a look at xn plus 1 equal to xn over 2 and yn plus 1 equal yn over 2, and we have x of 0 equal x0, y0 equal y0. So this is a system. But you can solve this and then show that the solution are stable. Well, I mean, let's take a v to be a x squared of n plus by squared of n. Or I can take something even easier, where a and b are to be determined. A, b are positive, are to be determined. So clearly, if I take xn plus 1 equal x, mean x over 2 equal x, mean x equals 0. Yn plus 1 equal y, mean y over 2 equal y, mean y equals 0. So we have x star y star equals 0, 0, which is the origin. Okay? So now we have a system. So this is the origin. So I'm going to let v equal to that. And so in other words, I'm going to let, I don't want to be, I want to vxn yn there. So that is my Lyapunov function now. So now that we have 0, 0 is our, and here a, b, and positive, and x star y star equals 0, 0. Okay? Now let's take a look at del v. That is ax squared of n plus 1 plus b of y squared of n plus 1 minus ax squared of n minus b y squared of n. Now xn plus 1 is xn over 2. So this is a x squared of n over 2 minus ax squared of n. I brought this a plus b y squared of n over 2 minus by squared of n. And that is minus a over 2x squared of n minus b over 2y squared of n, and that is minus a over 2 minus a plus b minus 1/2. Okay, so let me redo it. So this is equal minus 1/2 x squared over a plus y squared over b. Is that right? And that is always less than 0. Okay? This is less than 0 for a and b are positive. All right? Hence, 0, 0 is asymptotically stable. Okay? So here, I am taking my h to be xy belong to R2 such that x and y are positive. If x and y are positive, then this one is less than 0. Okay? So your x star, y star, which is this one, has to be in H. They have to be positive. So you cannot take, if you want asymptotic stability, you cannot take x0 equals 0. This will not work. Okay? If you take x0 equals 0, y0 equals 0, then you will always be stable, not asymptotically stable. All right. Any questions? Okay. Let's take a look at something that is nonlinear. Another example. Nonlinear. So this is example 6.5. We have xn plus 1 equal axn plus b xn over 1 plus x squared of n. And we see that x star equals 0 is the equilibrium solution. Okay? Now let us try v of xn equal x of n. Now there is one variable here. This is a scalar. Okay? That is a scalar equation. So del v of xn equal to, of course, xn plus 1 minus xn. That is axn plus bxn of 1 plus x squared of n minus xn. Now let's split the absolute value. This is less or equal to a xn plus b xn over 1 plus x squared of n. This one, okay, so that is equal to a xn plus b xn times 1 over 1 plus x squared of n. Now this number is always less or equal to 1. So this is, minus xn. Minus xn, yes. So I forgot to add minus xn. That's okay. All right. Axn. So what is that? So this is less or equal to a xn plus bxn minus xn, because this number here is less or equal to 1. So what is that equal to? A plus b minus 1 times xn. So this means if a plus b less than 1, we have asymptotic stability. If a plus b is equal to 1, we have a stable. If a plus b bigger than 1, we have unstable. You see the condition you have to put? Okay? Okay, next time I'm gonna stop here and pick it up. As I said, I will be done on Wednesday. So we didn't take a break, so I'm gonna stop here. And we will finish up tomorrow and Wednesday. All right? If there are any questions before I go off?
Professor, when we're having our final, is it on Sunday, Saturday or Sunday?
Yes, tentatively now it's Sunday.
Okay, all right.
Now, somebody is asking if the equation has more than one equilibrium solution, is the stability will be in the union of two? No, you have to treat each one of them separately. There's no relation between the two, okay? No relation between the two at all. All right? As we have seen. All right. Any other questions?
Yeah, hey, Professor,
Yeah.
how was the wedding?
Oh, it was wonderful. It was awesome. Yeah, the tent still in the background. It was the biggest, tallest tent I've ever seen, and like the one that they throw at UD. And it was a big tent. Everybody was comfortable. A lot to eat, drink, good people. So yeah, we had a good time. Yeah. So and the groom and the bride knew each other when they were 2 years old. So and I knew that we knew the families knew each other since 1999 when I moved to Dayton. We were living across from each other. So my son was 2 and she was 2 years old when they first met. And then, went off and then I guess they met again. Yeah, it was good. But Lily wasn't doing very well, I'll tell you that. I got Lily yesterday. And I'm gonna stop recording actually.